right, so RISC is a reduced instruction set computer. What does it mean for an instruction set to be a reduced instruction set?
Less cycles per instruction.
I don't know if that's more of a clock speed thing, probably. Go ahead.
It has less magic tricks.
Yeah, so all problems need to be solved in terms of a smaller total number of magic tricks. So we've reduced the size of the instruction set, so we have a less magic tricks, and then the compiler has a harder job to do that. So I mentioned one pro and one con. So what's a pro of reduced instruction set? Go ahead.
More battery consumption.
Battery consumption. That's been proved more recently since we have the ARM processors on mobile. Any other pros? Go ahead.
It could be faster.
Yeah, the same one you gave last time. It could be faster. It could be slow. Less heat. Less heat's a really good one.
Just generally less latency on the computer, which would be
Okay, fair enough. Fair enough. I don't think that's necessarily wrong. It's a little bit maybe vague, but that's fine. What about cons? Go ahead. Yeah, compilers are significantly more complex for it. And then we can go ahead and throw in your thing of it might be slower if the instructions that were produced by the compiler happen to not be very optimized because they were you're working within a reduced instruction set, and it just happened to be that that particular problem wasn't overly solvable in that situation. Any other cons?
Takes more effort to design a program directly in assembly, assuming it's a large program.
Yeah, so you're kind of playing the role of the compiler, I suppose. Yeah, that's not necessarily inaccurate. In some cases, and I don't think we actually discussed this last time, but they actually are in some cases harder to build. And part of that comes down to if you're the processor manufacturer trying to come up with the list of magic tricks that is appropriate for solving a general classification of problem without having too many. I mean, if it's a reduced instruction set, that obviously implies less instructions than an open architecture processor like Intel from the same vintage, let's say. So it implies that. Well, who's to say that you didn't need all those guys? Okay, so at some point, the person who's designing this particular architecture has to come up with, that list of magic tricks that they think will accomplish all general purpose tasks on a computer. So that's a little bit harder problem to solve as well. All right, make some sense? So anything in that ballpark of pros and cons, and as long as your pro and con is at least, I don't know, like it might be faster, might be slower. I'd probably take it since we talked about it in class and exploded it, as long as you had the rest of it right. So, but something along these lines is reasonable. Go ahead.
Could a pro potentially be that it's possible to be smaller / use less material?
Sure. I mean, by definition, it says a smaller instruction set, there would be less. Well, more. I guess I can't prove it wouldn't be less material. It's entirely possible they would just replace that material with more, heat reduction. But whatever. Anything that showed you were kind of thinking about the idea of size or heat or something like that is all fine. All right, so having said that, since now we have some of you have a bad grade on the quiz and some of you don't, extra credit opportunity tonight, Grace event, ice cream social tonight at 7 p.m. across the hall in the fishbowl, whatever. Do we have a scoop on the scoop on the ice cream? What kind of?
Probably vanilla, chocolate.
Toppings. Homemade blizzards.
No.
They're gonna have the blizzard machine. Hot wings. All you can eat hot wings.
Slushies?
No, so ice cream and some topping stuff. Okay, but this is the first Grace meeting of the year. So this is our Women in Computer Science ACM group. It's not just for women. It just happens to be that we're a chapter of that side of the organization. So men can be members of this group as well. And I strongly, strongly, strongly encourage you to attend the first meeting tonight. I think we're playing some games or something afterwards. Tournament Twister or something. I don't know. It was charades, something. But in any case, if you show up this tonight, I'll have a sign-up sheet, and you'll get an extra credit like token thing. And what I'll use at the end of the semester is I'll go through all your grades, and anytime you have something that's below 100, I'll take your worst grade, and that token will get you 100. So if you got a 0 in this quiz or a 30 in this quiz, if you're here, you come tonight, all of a sudden it's 100. But so it can't hurt you because this is the extra assignment. It's just it'll undo a mistake later on. Yeah.
If you show up like really, really late.
Well, how late's really late?
Well, I don't know how long you guys are planning on having it go, but I work, and if I get cut early, then I will. I'm
guessing it's like an hour.
Yeah.
So 7 to 8. Yeah. So I mean.
I showed up at like 7:55.
I would say probably not, but there will be other extra credit opportunities this semester. So, all right. So that is tonight, 7 p.m. across the hall in the old fishbowl. Show up 7 p.m. Probably be there on time is the most important thing. If you have to ditch a little bit early, that's less of a big deal. But I want to make sure everybody's hears about what Grace is and what the plans are for the rest of the semester and all that jazz. Anything else you wanna add, plug?
You really don't have to be all that early.
No, just on time. I want them there on time. Yeah, on time. Be on time. All right. So.
Bring your phone.
Huh? Bring your phone. Oh, for the trivia.
Yeah.
Is Mr. Gonzalez invited?
Yeah.
All right. He loves ice cream. Yeah. All right. So, Mr. Gonzalez will be there.
I'll wait outside there right after class.
Just pining. You camping out for the ice cream social. I'll give you extra credit. If you literally after this class you have to like check in often, so it's like I could see the time stamps or something. You literally camped out for the ice cream social. And as people are coming by, tell them they should come for that thing.
Advertise it, hold up a sign.
Yeah. I mean, extra. That's 3 tokens.
3?
3 tokens.
I'll consider it.
Well, if he's camping, he needs a tent.
Well, he doesn't need one.
Well, he should have one.
You could have ammo.
Perfect to go from hallway.
Yeah.
I came to safety filters while you're in the hallway.
Okay. So that is tonight. I hopefully will see most of you there. Okay, so we talked about the whole RISC open architecture stuff last time. I've thrown this slide in here so I don't forget it. We're going to be trending towards this discussion of ARM processors this semester. We're going to be doing some assembly programming in ARM, and I also mentioned that we're going to be writing probably an Android app, but if you really, really wanted to do an iOS one, that's fine. I don't care, some mobile app. But in class, we'll do it as an Android app, where we're going to write our own assembler for ARM to understand how that works. And it actually is significantly easier than it sounds like it might be. So it kind of gets us that idea of if you were the one creating a microprocessor and implementing those magic tricks, how does that process actually work? So it shows us those different handoff things and how the interaction between the various caches, memory, stuff like that, all playing into instructions and things like that. So by having that implementation, a simplified implementation, we'll be able to see how those moving parts actually all talk to each other, what are the advantages, and that kind of stuff. Okay, so for a few minutes here, I want to bounce over here to in our chapter 1 in our book. I think I referenced this last time. Everybody has the book now? Ish? Has the book ish? All right, so this is probably something you've heard of before. How many of you have heard of Moore's Law before?
Yeah, they double the speed every 18 months.
Yeah, so this guy right here says, Moore's Law states that integrated circuit resources double every 18 to 24 months. I think that's less true today than it has been historically. That doesn't mean we're not still increasing relatively rapidly, but I think we've started to hit some walls in terms of how much we can squeeze into the same space. And now we're looking at alternative approaches to it, but that doesn't mean that we can't come full circle back to this idea. And, you know, when we have our next breakthrough in technology, I mean, kind of roll back, and computers were not overly impressive or getting substantially, I guess I'll just use the same phrase again, substantially more impressive until the advent of the transistor, right? And then we got better and better and better at making the transistors smaller and smaller and smaller. And now we have zillions of transistors onto a single chip, and it does a whole bunch of stuff. So what's the next leap when we move from like a vacuum tube to the transistor? So, and we'll talk about some of those things in the past, but we effectively went from the equivalent of a light bulb for on off to a switch that's a transistor that we started off making as a larger thing, but still smaller than the vacuum tube. And then we were able to miniaturize that to something that's very, 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 very tiny. Okay, so what comes next? What's the next transistor-like thing? Is it something with quantum computing? I don't know. We'd be making a guess, but at some point it'll probably happen. Is it possible that we're at the end? That it's not going to get any better than this? It's possible. Who knows? But it seems like every year we come up with better ways of doing the things that we're already doing, and it's just a matter of time before we kind of jump past some of our heat wall stuff that we have and, you know, make a big move forward. So I wouldn't throw Moore's law out the window, but it's giving us diminishing returns at this point, but still something to consider in general. Now, from a computer architecture perspective, if you're building other parts for a computer, even if it's the CPU, but if you're building the CPU or you're building memory, why is the underlying concept of Moore's law important to you? If we just operate off this idea that our computers are going to keep getting faster, regardless of the rate at which they get faster, they keep getting faster, and you're a researcher coming out with the latest, greatest memory architecture. What are some things you have to keep in mind? Go ahead.
Well, things are probably going to change pretty quickly after you release whatever you're coming out with, if not even before it's fully released. So you need to constantly be thinking about is this going to apply in the future?
Mm-hmm. And a lot of times in our computers, and we're going to see this when we start looking at how all the different parts really connect with each other. We've mentioned it already with buses, and where there's these different speeds that things talk to each other, and within at least for some of the technologies, there's a compatibility that's necessary for those speeds. Where if you have RAM that's really, 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 really fast, and the guy that's talking to the RAM is relatively slow, all of a sudden you're only going to move as fast as the slowest of those two. Okay, so why get the super fast RAM if the rest of your system can't keep up with it? Kind of makes sense. So Moore's law, kind of an important thing to keep in mind in general, but it's not all that meaningful other than just telling us that technology keeps getting faster and faster and faster. So watch out. You learned about this in 150, the idea of abstraction. What is abstraction? Yeah, simplifying. Didn't you have Einstein simplified? The cartoon of Einstein? That slide has been there forever. I mean, I've been here this is, I think, 13 years. And I think that slide was a pretty old slide then, is my guess. But so it's simplifying a problem. So we're abstracting a problem. That's an important thing for any sort of, design. But when we talk about hardware, we're getting millions and billions of these things squeezed into a very small piece. Sometimes abstracting problems is a pretty important concept when we have to talk about this component talking to this component, talking to this component, talking to this component. And then you realize that all those components actually live inside of the actual CPU. And the actual CPU is not what we think of as being that big square. Most of that is silicon and communication between multiple cores, and cache memory is built in there, because a lot of our processors today have 4 cores or 6 cores. So there's actually 4 or 6 actual processors on that. So we really need to abstract that problem when we talk about those things communicating with each other. A big thing for us, something we're going to talk about quite often as we go through the semester, is making the common case fast. One of the things that, and you're going to see this, this kind of goes back to this whole idea of the grand ideas of computer science, where we see a lot of the same trends in different classes. We have the same conversation, but from a different angle in a different class. So operating systems comes to mind with this idea where if our overarching goal is to make an operating system fast, whatever that means, what does it mean for your operating system to be fast? We have to kind of take a guess at how users are going to use the operating system. How many applications they're going to have open at once? What's the nature of those applications? How are those applications going to work with other applications that are on the system, work with things that are in the that are built into the operating system? We're making a lot of guesses at how will the average user use this operating system. It makes some sense? So they try to then make that common case the fastest case. For those of you who work in like the IT department or have done something with building machines and stuff like that, this is kind of an interesting punchline to something that's been around for a while. What's the difference between Windows 10 and what's the equivalent server for Windows 10? Is it Server 2017? Microsoft Windows Server 2017? Whatever it is.
Isn't it just 10 Server Edition?
Is that what it's called?
I think so.
Prior to this, I thought there was a Server 2013. I thought there was a 2017. Whatever it is. Windows Server Edition's good enough, whatever the name of it is.
Server
Okay.
2016.
Okay, Server 2016? Okay. So what's the difference between Windows 10 and Windows 10 Server 2016? Whatever. Because I promise you, they both have the same Windows 10 kernel, the same core operating system. What's the difference between those two? Yeah.
It's implemented differently in the style processor. Normally like the Xeon server class processor, which
Okay.
only has,
But would Windows 10, if you just took a normal Windows 10, would install on a Xeon machine?
yeah, it just might not be as efficient as
Okay, so if you consider that your operating system might have some little tweaks, almost thinking about it like when you have a video game that has the different graphics settings. I want to run it in low graphics, ultra settings, whatever it is. You have these different things. It's almost like that, where they've gone through, they've tweaked the OS to be less about a single user dependent decision making to now a multi-user dependent decision making, which can go to how it does. What are the common processors that might be working with? How are users interacting with the system? What built-in things are part of the distribution? A lot of the server stuff comes with your telnet servers and your SSH servers and web servers and all that stuff.
like having multiple CPUs.
Sure. But those things are available in Windows 10, but the whole scheduling algorithm might be different on a server type environment, because it's going to be much more common that you're trying to make 10, 20, 30 simultaneous users happy instead of having one user you're trying to make happy. So even though it's the same underlying OS, different things have been tweaked to make the common case, what they believe is the common case for that, fast. And what you're going to start seeing more and more of in the future, before instead of just giving you the punchline, what do you think is going to happen? How do we come up with that common case? How do we decide what is the common case for operating systems? Like, how is the average user going to use Windows 10? How do they decide that?
Use of analytical data.
Okay. So your computers are all kind of gathering information kind of anonymously of the stuff, how people are using it, and they're sending it back, and then they're looking at that data in some way and making decisions?
I'm sure at some point, yeah.
Okay. So, and that kind of tries to capture the average use case across the entire population of standard users, or the entire population of server users, something like that. Okay. How might that change moving into the future? How do you perceive things are gonna change for making things faster?
Well, the components could get smaller.
I'm thinking more about this decision making about what the common case is. This is another example where we have, the various ideas in computer science starting to collide with each other. Go ahead.
If everything keeps getting faster, people may start using programs that are more demanding on a regular basis.
Well, that'll change the nature of how people might be using the computer. I'm talking about how might we see an evolution in how the analytics works for determining how do we need to evolve our operating systems to make them more, make them fast for the common case as the common case changes. Go ahead.
Probably start using more of AI and things to
Yeah.
analyze the data and figure out what does it look like if we tweak this, what does it look like if we tweak that.
So a lot of machine learning stuff that is able to deal with large data sets and processes as it comes in. And a second advantage of that is you can have an operating system that through AI gets better at serving you, the way you use your computer. So if you take that collection of switches that, we can tweak a little bit more memory use here and a little bit less here and a faster clock speed here, all these little things that we say are tweakable in the operating system. And then we attach an AI to that and start saying, we're going to collect information about my user, okay, the person in front of me. And I'm going to make little decisions based on how what that person's common case is. Because maybe I use my computer differently than you use your computer, so on and so forth. Or maybe as technologists, maybe we use our computers as a collective group in a different way than maybe your global average population might use their computer. Where you're having, a whole bunch of grandparents and stuff like that in there who check email and Skype. Those are like the two things that they do, and that's now getting thrown into the averages with everybody else. So we're going to be moving in a direction, or it seems to me we're going to very likely move in a direction where our machines are going to get to know us better and better. And we've already started seeing it happen with our phones, right? Kind of a related thing to this is many of you know I'm a very avid golfer. So my phone tries to determine where it thinks I work. Do you know where this is going? So during the school year, it does identify Concordia as my place of employment. During the summer, about 3 weeks in, it believes I've switched jobs. Because I golf over at River Club, the country club up the street. So I always golf at the same place. So I'm a member over there. And I play every day. So I'm going to work. So my wife will get a message because she has this other thing set up on my phone. So she knows like when I arrive home or arrive at work or something like that. So she'll get a message that I've arrived at work. And during the summer, that means I'm at the golf course.
It's like tracking your movement.
Well, yeah, somebody's got to be able to find me if I get lost.
Has it ever gotten to the point where it thinks the golf course is your house?
Not yet. I haven't seen home change.
Okay.
But it's possible that when you first set up your phone, you had to put in your home address. That might not be a changeable thing. But it is a fascinating question. You've gotten an issue.
Well, what if you move to the golf course?
That's true. With the GPS, how would it be able to granularly? If I did move out there, there's a plot of land that's like probably maybe a 4-minute walk from that house. But I'd probably have my own golf cart then, so it's probably only a 30-second golf cart ride. Wouldn't that be awesome? If there's like just decked out golf cart, put awesome fat logos all over the thing, and so good. Golfer Bubba Watson has a hovercraft golf cart.
What do you mean by hovercraft?
Well, you know what a hovercraft is? Like the things that can it's like a tank looking thing, but it can go on lakes. No. It's that. Yeah, it's got an air bladder thing underneath it, so it can go over all sorts of terrain. He had this company build him a golf cart on top of a mini hovercraft. He drives around his home golf course. It just drives it right up on the green, no big deal. It's like there's no tires. Yeah, so in any case, we're already seeing AI make some of these decisions. So we're seeing it creep into our lives already. And I think it's just going to become more and more and more where it's making decisions for us that we didn't even know, we were making. I think my phone now, it tries to detect or determine when you typically get in bed. And I think there's a setting in here, I think I have it turned off, but where it'll automatically put on the blue light filter when it thinks you should usually be in bed. That way, because there's the blue light supposed to make you stay up, like it's harder to fall asleep or something like that when we get in bed and play on our phones for an hour and a half. Yeah, so in any case, this idea of making the common case fast is a really important thing in architecture, but it's actually it's a constantly moving target. What is the common case? That might be an easier thing in very small moving, small magic tricks, but as a general purpose use of our computer, that keeps changing. So it's very easy to say make the common case fast, but then we have to ask ourselves, how do we determine the common case? So that becomes another thing to discuss. Parallelism. This is a big deal, and this is how we've seen our processors evolve over the last many years, especially as we started hitting the heat wall. So even as processors kept getting faster and faster and faster, we had computers that were dual CPU computers, where they physically had two separate processors. And that's been around for a while. We couldn't fit any more onto a single chip, so we give two separate chips. And these were even single core processors where you had two of them. This kind of reminds me of it was Apple. It was a PowerPC, so it was a RISC processor. The Apple G4 processors. They had these commercials where it was the first supercomputer at home. So Apple had these commercials where it showed the like tanks driving around that said G4 on the side of them and all this stuff. And I had a Macintosh G4. One of my hobbies I had a Linux machine and a Windows machine. One of my hobbies was networking these guys together and making them all talk to each other. Share a printer between all of these guys back when these guys were not compatible with each other at any sort of level back then. So I had a G4 machine, and I sold it right at the right time too, because I sold it on eBay. This is in the early days of eBay. And then like a week later, Apple announced the dual processor G4s at the same price point as the single processor G4s. So I ended up getting one of those and almost paid for it because I just sold the single processor one the week before. So these are still single core CPUs. So each CPU only had one core in it, which means it could only technically do one thing. But now we had two separate physical CPUs. Okay? Now, this is back when Mac OS 9 was the operating system on the computer. Does anybody know what's kind of funny about this this idea of having I think all the commercials would say like two heads are better than one or something like that. So you have this motherboard that has two G4 processors on it, and you buy this brand new Mac that super expensive, whatever it was, $4,000 or something, and has and is running OS 9, Macintosh OS 9. What's funny about that whole scenario?
OS 9 doesn't have multi-threading.
Multi-threading, it did-ish. It had multi-threading. It didn't have multi-processor support. So you have this OS that natively could not use the second processor. So they came out, and what makes this really funny is, especially today, we think of Apple as being this company that everything just works and they really think things out really well and all this stuff. And that's more true now than it was then. I think it's less true now than it was 4 or 5 years ago, but whatever. I mean, things have changed. But so it's very interesting. They come out with this brand new computer that they're just advertising the heck out of, yet they have an operating system that can't take advantage of the brand new thing that this guy came out with. Like literally your CPU would sit there completely idle because the operating system could not take advantage of it. There were specific applications that could leverage the second CPU. Okay. So like the one in the moment was Photoshop. Photoshop could take advantage of the second CPU. So if you were a Photoshop person, you lucked out. The computer wasn't a complete waste. Once OS X came out, then it could support both CPUs, and that was better. But now those CPUs were it was old news and older technology, and they probably already had 2 more releases of those CPUs before OS X actually hit the market. Just kind of a funny thing that they would release a brand new computer that couldn't efficiently utilize their own software. So then they went and they acquired Next Computers, and that came with the OS from them, which they put Aqua on, which was the Apple front end to make Next Computers' Unix-based operating system look like a Mac, and that's what we call OS X today. Okay, and I think you've heard it from me in other class that really what we call Apple today is Next Computers with an Apple logo on it. It's even in their APIs. A string inside of Objective-C is called an NS string, next step string. So it's throughout there. They acquired the company. Steve Jobs came with that acquisition, and they threw the Apple logo on top of Next Computers, and the rest is kind of history. But today, it's very much commonplace for us to have parallel processing, right? You can't even buy a general purpose computer today that has less than 2 cores in it. In fact, most of them anymore have 4 cores. You'd have to go the lowest end chip in order to get just a 2-core processor. Now, understand there is a difference between multiple cores in a single processor versus multiple processors. Does that make sense? So let me I'm going to create a slide for this guy. Parallelism. Oh, is that right? It's not screaming about it. I'm shocked I got that right. Okay,
There's another out.
Parallelism III. Parallelism. Here, I'll say parallelism in CPUs, because that's really what I'm talking about here. All right, so we have a couple of options here. So we have single core CPU. Now, when I say CPU, I want us to think about the physical processor right now. Okay, even though there's a gray area in there, but if I held up a Core i7 chip in front of you, and I have this, this square, that's what I'm calling a CPU, even though a Core i7 is going to have at least 4 cores inside of it. Okay, so a single core CPU versus a multi-core CPU versus a versus a single CPU versus I actually think there are machines that they're less common now, but there were machines that had like quad CPU setups on them. But let's just say dual CPU for our example. All right, so a single CPU versus a dual CPU indicates the number of physical CPUs we have present. When we add the word core in there, we're talking about the number of cores that exist within a single CPU. And a core we can think of as a unit of computation. Okay, so every single time we have a core, we're talking about another instance of the instruction set. Cores. An instance of the underlying instruction set or architecture. All right, so when we have a quad core i7 processor, we have 4 instances of the i7 architecture living within the single physical CPU. And that means that 4 things could technically happen at once. Now, how many of you have ever seen this thing called logical cores? So, for instance, if you were to go out and look at a, we're going to say quad core, Core i7. So we would say, oh, that can do 4 things at once. But so they said it's quad core, but they would say this guy has 8 logical cores. What does that mean? It's a quad core processor, so that means it has 4 instances of the Core i7 instruction set. But what does 8 logical cores mean? Is it just a way for them to say we're going to double the speed? It's like we said 4, we meant 8. Anybody know what it means by logical cores? It used to kind of be attached to a buzzword that Intel kind of came up with. And now they're all using the kind of similar buzzwords, so we don't even acknowledge it being related to the buzzword anymore. How many of you have ever heard of hyper-threading? Oh, yeah. You get a processor with hyper-threading in it, it's got to be better than a processor without hyper-threading. What is hyper-threading? We would say, I'm going to put this in terms of something we're going to talk about in here. This is an implementation of pipelining. Pipelining. Spell that right? Yeah, close enough. Okay. Implementation of pipelining. So pipelining is a way of getting instructions kind of interwoven together in such a way that we can get them onto the CPU more quickly than they would get loaded on the CPU otherwise. It does not necessarily give us twice the speed. It instead enhances the speed that we would already have on that particular core. All right, but it sure sounds better to say 8 logical cores. And it certainly is faster when you're using 4 cores with a pipelining implementation for each of the cores. You are then able to increase the throughput of instructions through those cores by something. And the better the technology we get, the more we're able to increase it, but not up to the point of twice the speed. Anybody know what AMD's current hyper-threading competitor is called? I like this one.
Threadripper?
Threadripper. Doesn't that sound way better than hyper-threading? Hyper-threading sounds like, like a PG movie. Threadripper. I mean, that's like a horror movie, right?
What if we just split the difference and just call it Hyper-Ripper?
No, I don't like Hyper-Ripper. You gotta have the word thread in there. Thread sounds cool. Intel with 7th generation Thread Annihilator. What was that? Oh, from the movie Idiocracy. How many of you have seen that? I've referenced it in other classes before. Brondo brand, they have these commercials. If you look up Brondo on YouTube, you'll see some funny commercials that I can see Intel coming out with commercials kind of like those are, where they're like really talking about like what their new threading technology can it's like running Microsoft Windows with the monitor off, stuff like that. If you watch the video, that'll make sense. Yeah, so Threadripper is their current thing, which I think sounds kind of cool. But a lot of times you'll see this reference as logical cores to give you this concept that you actually have 8 cores instead of 4, and there might be some performance situations where it can act as if that's true or close to true, but that's not an all the time thing. It's really going to depend on the nature of the pipelining. Okay, so when we talk about cores, we're talking about an instance of the underlying instruction set. So that means that the more instances we have of the underlying instruction set, the more simultaneous instructions we can process, right? Because we got, in a quad core setup, we have 4 dudes that know how to take an instruction and perform a magic trick. So we can have 4 different magic tricks being performed simultaneously. Now, is 4 cores better than 2 cores? Depends, right? Depends whether more cores is better than less cores. What about when it comes back to an operating system perspective? If you're writing an operating system for a single core processor versus writing an operating system for a dual or a quad core processor, does the operating system become more complex? So this is similar to the conversation we had last time about compilers being more complex when we have to write them for a reduced instruction set architecture, because it's a harder problem for them to solve. They have to squeeze that high-level language into fewer magic tricks, and that's kind of a complex task, at least from an efficiency or an optimization perspective. If you're creating a operating system to schedule tasks on 4 cores instead of 1 core, let's say, why is that more difficult? We can do 4 things at once. Why does that have to be any harder? Can't we just say, oh, here's an instruction you want to do, I'm just going to send it to the guy that's not busy? If you think about it from like the McDonald's example, people walk into McDonald's during lunch rush, there's 4 registers open. You walk to the register that's least crowded, right? There's an available register, you go to that one. Otherwise, you get in the shortest line. Why is it more difficult than that when we talk about operating systems?
Because sometimes certain things need to be done before the other calculation be done. Like, you may be able to do this now, but you need to wait for all these to finish first.
So when I walk into McDonald's, what I order isn't dependent on what the lady over there is ordering, right? So it's okay for me to just go up to the empty register and start placing my order. Okay? But if instead what I was doing was in terms of something that she was having done, I'm not going to be able to place my order until her order is complete. Does that make sense? So now you break that down into individual instructions on an operating system. There might be an instruction. We might have an available core that could process an instruction, but it actually can't be scheduled to process that instruction yet, because that instruction is the next instruction for an application that is waiting for the previous instruction to complete. Make some sense? And now we have to build into our operating system the logic to determine all that. That's a lot of stuff. So our operating systems have gotten more and more complex over time because of those types of things. So we're seeing these patterns that exist in all sorts of different fields inside of computer science. Just because you have a processor that can do 4 things at once doesn't mean that your processor will do 4 things at once. Okay? In fact, most of the time, your processors sit there idle. Most of the time, they sit there idle. I mean, you can find percentages out there, like 98% of the time your processor's not doing anything. And if your machine's on all the time, that's probably a true statement for most users. But if you're using your machine for gaming or something like that, and you're playing for 10 hours, well, during that 10 hours, your processor was working pretty hard. It was not sitting there idle for 10 hours. It was working pretty hard for 10 hours. But it all comes down to the averages. But in general, we're not taking full advantage of our processors when we are using our computer. So when somebody goes and buys a new computer, you have to think about, so if you're giving advice to somebody who's buying a computer and they want to know, oh, well, here's my budget. What do I spend my money on? So let's say that they have a budget that is reasonable enough, but not so much they can just max everything. So what's probably the most important thing for realized speed on a computer? Should you get the Core i7 processor or should you get the Core i5 processor? Depends what you're doing. But for the average user, i5 is going to be plenty, right? They probably won't notice a difference. What should you then spend the money you're saving from the i7 on? What should you up next?
RAM or storage speed.
Okay, so you need to have enough RAM, right? So first of all, you got to make a pass and get everything up to whatever the minimum is that they need. So maybe you say that the average user today needs at least 8 gigs of RAM. If I was building a machine today, I probably wouldn't put less than 16 in it, just because you probably want to use this machine in 3 years. So in 3 years, 16 is probably going to be the norm. So, put 16 gigs of RAM in it. It's not overly
be able to run Google Chrome.
Right.
So
Right. Right. So it's not expensive. 16 gigs of RAM is fine. I would get whatever the A reasonable speed processor is, but based on what you are going to use the machine for. And then I would spend a majority of your upgrade money on hard drive speed, because that's where you're going to see it the most. If you get a if you max out some computer, let's say you go and get a desktop computer with I don't know, just pick some Core i9 processor, so Intel super crazy expensive 32 core. Did I say expensive? Say it 20 more times. Processor, and you're going to put, I don't know, we'll put 2 terabytes of RAM in it. You know, why not? You know, we'll just put 2 terabytes of RAM. Not going to use it ever, but we got it. Okay, so they have 2 terabytes of RAM in it. And then you go out and you get a 2 terabyte Western Digital mechanical 5400 RPM hard drive.
2. You mean 10?
No, 2's fine. 2's fine. It doesn't change my example. So you have a 5400 RPM mechanical hard drive in what is otherwise a supercomputer. The person who's using that computer is going to feel their machine is sluggish because of that hard drive. That's what you'll feel as a user, assuming you have enough memory. The thing that you're going to feel the most is that hard drive speed. So you're going to want a solid state. The faster the speed of the solid state, the better. That's where you want to spend your money, because that's where we have realized speed. That kind of makes sense? But if you're a normal consumer, you don't know about the underlying hardware stuff, and you go into Best Buy to buy a computer, the first thing that catches your mind, your eye, is going to be the processor speed. You know, you almost think of that like if you're buying a car, it must be the engine, right? You know, like, oh, V8's obviously better than a V6. But even then, you know, car people are going to kind of be able to tell the difference between that. But if you're somebody who just goes grocery shopping, do you need a car with and you live in an area that never gets snow? Do you need a car with a V8 engine? You live alone? You don't need a big car. Oh yeah, I'm gonna get one of those smart cars. We're gonna reinforce. We're gonna put a Corvette what is it, V10 or V12, whatever is in the V12 engine in the smart car. You got to wait down the back to make sure the thing doesn't just nose over. So it's at some point, as if you're like a car enthusiast, like Dr. Locklear is a car enthusiast, so he could probably have these conversations. As long as I fit, I'm good. I don't care about the speed of the car or anything like that. But you know, so I would be more like that average consumer, right? Maybe I know a little bit about like, oh well, you know, the bigger the engine, the worse the gas mileage or something like that in general, right? But punchline is I'd be more like that average consumer when dealing with cars than I would be with computers. So your average consumer goes into Best Buy and they say, oh, I want a fast computer. What does fast mean? But the first thing that's going to catch their eyes are the things that have fancy sounding names. AMD, Ryzen, Ryzen, whatever. How do you pronounce it? R-Y-Z-E-N? Is it Ryzen or Ryzen? Ryzen? Ryzen with Threadripper.
As in House of the Rising Sun.
Okay. Now, if you're a consumer and you see something that has all these like buzzwords on it, up to 3.9 gigahertz turbo boost, Ryzen, Threadripper, 68 cores, blah, blah, blah. You're going to be sold. Okay, right afterwards it says, 3 gigabytes of RAM, 512, 4200 RPM laptop hard drive, refurbished. all these other things that lead to it not being all that great of a machine. But those are the things that attract us. So as technologists, we want to understand how these underlying parts work to have conversations about these things. Okay. So punchline with parallelism is more is not necessarily better. We also already kind of talked about pipelining, where we can stream. That's the hyperthreading aspect of those things. So we can streamline stuff through there. We've also talked about this performance versus via prediction thing, where that we had that conversation along the lines of the common case fast. We have to predict how the user is going to use the machine in order for us to determine what the common case is. Okay. Now, this also speaks to a kind of another thing that happens in our computers. If we do have cores that aren't sitting there doing anything, and we do have enough cache memory, we have resources that we're not otherwise using now. What we can do is we can make a guess as to what, for instance, instruction might come next. Okay, so we can guess ahead. You know, we might be on the back side of a branch condition, so it might be an if statement, and we might make the guess that the if statement will fire true. And if it fires true, the next instruction will be this one. But if it fires false, we guessed wrong. So now we're not really ready. We have to go and fetch the next instruction, and then we have a slowdown. But otherwise, if we had pre-fetched the instruction, so it's ready to go, and we happen to guess right, we just sped up the performance, right? We already had the resources to do that. So we have this prediction, these various points inside of our computer and also inside of our software where we're predicting what's the next thing. We have a place to store them. Sometimes we can speed up our computer if we guess right. Going to make some sense? All right, memories. Oh, it's all inside here. So we're talking about these at the high level. What is memory? I mean, when we talk about memory on our computer, what kind of things are we talking about? What are things that are memory?
Variables.
Okay, so that's more from a programmer perspective. So variables will get stored somewhere in real memory. What's a generic definition of memory? What does memory do?
Short-term storage.
Yeah, hold stuff. Short-term storage, I like that. Let's just say hold stuff. Because actually, I don't even know if I want to say short-term storage, because I think, for example, I think I would call a hard drive memory. It just is a certain kind of memory. So memory holds stuff. So when we think about holding stuff, what are the when we think about kind of measuring our memory, what are some things that come to mind when we talk about memory? What makes one memory better or worse than another memory? Size. So capacity. Care about capacity. We care about speed. Anything else? Is that really our two things?
Cost.
Yeah, cost is true. Yeah, so we do care about that. And actually, that is really important. That's going to be part of this discussion anyways. So capacity, speed, and cost. Yeah, we want everything to be reliable, but you're right. You're right. So generally, if we have a hard drive where we're talking about storing things long term, we expect there to be a larger capacity than we have an expectation for our system memory, which we would expect to have a smaller capacity. Might be common today to get a new computer that had a 2 terabyte hard drive in it. Or if it's solid state, maybe it's a 1 terabyte or a 512 gigabyte, whatever it is. Terabyte hard drive or solid state hard drive. Yet it has 16 gigabytes of RAM, far less RAM. All right. Now, just to review this stuff. Okay. So when we talk about the different sizes of these things, we have bits and we have bytes, right? And hopefully most of you have seen this before. What's a bit? What's a single bit? 0 or 1. What's a byte?
8 bits.
8 bits. All right, so a byte is 8 bits. What is a kilobit? 1B.
1024 bytes.
1024 bits. Bits. Okay. It's going to be extra important in this class because we are going to be dealing with zeros and ones at the bit level. So small b means bit. 1 kilobyte, big B, is equal to 1,024 bytes.
Oh, I know.
1 megabit, small b, is 1,024 kilobits, small b. 1 gigabit, small b, is 1,024 megabit, small b. 1 terabit, which actually is not a very common thing you will hear today, but eventually it will be, is equal to 1,024 gigabit, small b.
When do you think we're gonna have terabit internet connection?
Well, right now we have some gigabit internet connections, and then in enterprise you probably have up to 100 gigabit connections. So within 10 years probably be my. I mean, I'm pulling that number out of the sky, right?
Well, I was wondering less than or more than.
Yeah, I mean, you just look back in time. In let's see. What year would that have been? Like 1998, somewhere in that ballpark, 1998, let's say. A 1.44 megabit per second internet connection, which was called a T1 line, would have cost something like $30-some thousand a month. It was something that, enterprises had that you bought from the phone company, blah, blah, blah. And it was called a T1 line. So a lot of places, they wouldn't do a full T1. They would do a fractional T1. So a fractional T1, you might get, 300 kilobit per second for maybe 10 grand a month. 300 kilobit. Now, even if you were getting the full T1, how much slower is that than our modern, what's our budget pleaser internet connection today? With Spectrum, I think offers 100 megabits is their cheapest. 200 now. Okay. If you go through like AT&T, Uverse, are using a different technology, and we'll talk about some of that stuff, but I don't want to get into it right now. Can I do math here? I usually do this on the Mac. So can I do 200 times? It will work. It won't work. Well, that's fine. All right. So if I have 200 megabits, that is 200. Well, what I'm going to start off by doing is I'm going to do divide by 8. So that's 25 megabytes per second is your speed that you can get. And if we want to take that down to K divided by 1,024. So, multiply by 1,024. So you'd have a download speed of 25,600 kilobytes per second. Pretty good. what was it before the 25 megabytes per second max speed? It's not bad. That's if you got full speed from someplace else. As opposed to, if you're downloading at full speed, as opposed to if you had 1.44 megabit divided by 8, you're getting 0.18 megabyte times 1,024. So you could get 184K a second for 30 grand a month. How much would you pay for that?
30 grand a month.
Back in 1998. Back in 1998, speed was, so, we kind of do the math, right? So that's 20 years ago.
It's even more than inflation.
Well, yeah. In 20 years ago money, it would have been even more. You're right. So if we fast forward 20 years, what are our internet connections going to look like in, so if we forget about the dollars and we just scale the time. So if our fastest internet connection back then, I mean, this was something that was completely unaffordable, but let's just say it was 1.44 megabits per second. And today our fastest is for consumer, well, heck, we're not even talking about consumer, but let's just play that game. We'll say it's 1 gigabit. So 1 gigabit is 1,024 megabyte, or megabit rather, divided by 1.44. So our internet today is 711 times faster. The fastest consumer internet we can get today is 711 times faster than it was 20 years ago. So we divide that by 20. So now we're at every year we triple. On average across that time, there was a ramp up. Well, not triple, 3,500%. So 35 times our speeds. That means if this year we're at 1 gigabit, next year we should be at 35 gigabits. For maximum consumer internet, I don't think we'd see that. But keep in mind that was stretched over that period of time. Now, if we look at a much shorter period of time, what were our internet connections in the last, let's say, 5 years? So how long have we been able to get 100 megabits per second? Quite a while. So what is currently the cheap internet, 200 megabits per second, was the fast internet 3 years ago. So if we operate off of that, if the fast internet is 1 gigabit today, then the slow internet in 3 years will be 1 gigabit, and the fast internet will be 5 gigabits, something like that. Probably scale up from there. So if we're just trying to make guesses off of that, so then then I go back and think about my terabit comment. I don't know. It's a pretty big jump unless we're looking at enterprise.
15, 20 years.
I don't know. Enterprise for data speeds really goes up fast. I'm going to stick with my 10 years.
All right.
I think that's a thing. All right. So 1 kilobyte's 1,024 bytes. 1 megabyte, big B. Okay, and I really want to encourage you to pay very, very, very close attention to whether we're looking at big B's or little b's. Okay, little b's means you're dealing in bits. Big B's means you're dealing in bytes. Okay, and that's an important thing when you have to do math with these, which we'll be doing a lot of in here. So 1 megabyte is 1,024 kilobytes, big B. 1 gigabyte is equal to 1,024 megabytes, big B. 1 terabyte is equal to 1,024 gigabytes. So on and so forth. And I think it's what? It's a petabyte, and a exabyte, and I don't know what comes after that. It's something. There's names for them for a while.
Yodabyte, zettabyte, yodabyte.
Zettabyte, yodabyte? That sounds made up.
No, that's right.
They just said, look, if we get there, they'll find it funny. Or they won't remember who Yoda was.
Well, it's YOTT.
Doesn't matter.
Yoda's for-
Doesn't matter. It still sounds like yodabyte.
Yeah.
All right. So this conversion stuff is going to be important. I'm going to ask you conversion questions very, very often, so you should be able to convert between sizes. This is going to be pretty important for us. For example, if you need to store, let's say we have a 6, well, let's operate it. Let's say we have a 6 or an 8 gigabyte RAM chip. And I ask you how many bits are in 8 gigabytes. How would you do that math? How many bits in 8 gigabytes?
Just figure out how many bytes and then multiply by 8.
Okay, well, so right off the bat, you can jump it over to the other station by multiplying by 8, right? So this is actually 64 gigabits. And then we multiply it by 1,024 to get us to megabits. So 64 times 1,024, that's megabits, times 1,024, that's kilobits, times 1,024, that's bits. So that's 68,719,476,736.
Pretty small number. You didn't want to get that out yourself.
Bits.
Is that more than 2?
All right, so that makes sense? So you should be able to do conversions across this chart. So spend some time making sure you understand. I mean, I say memorize this chart, but it's not a difficult chart to memorize. Everything scales by 1024. The only thing you really need to memorize is the bits versus bytes, factor of 8. So be able to do math across those because we'll be doing that quite a bit. Or a byte, quite a byte, yeah. That was a good one. All right, so memory, we think about it holding stuff. We think about capacity. We think about speed. We think about cost. Now, what about kinds of memory? In general, we might say that the larger the capacity, the slower the speed. Those tend to be related to each other. That doesn't mean if you don't factor in dollars underneath there, if you just forget about the cost side of things, you say, well, we got, 16 terabyte hard drive-ish that we've had custom made for us completely out of L1 cache. It's ridiculously expensive. It's hand soldered on the island off the coast of Finland or something like that. Those always makes it better when they talk about something being handcrafted. Like, why is that better? Like, wouldn't you rather have a machine that had like a lot of precision to like make something like that's important? It's like, instead of like, there's somebody like whittling something out of stone where they 10 of them, they don't, they're not making the same thing. Like in these movies, they talk about, they made this, my dad built that log cabin by hand. It's like, oh, well, how much longer is it going to stand? If you had that thing 3D printed, it would be way better. How long until we're going to be 3D printing all of our houses?
That's a little way,
they're doing it already.
Define all of our houses.
They're 3D printing houses already.
How long was that today?
It's like an afternoon. They have like it's not a giant house yet, but they have a thing that they come out and
It's a pretty good size.
Yeah, I mean,
Like the size of this
just
room.
print your house.
Nozzles like this big.
Yeah, so good.
I'd say 5 years before we see a company dedicated to
3D printing houses.
right. And so then the question is, how long do they take to get like a large amount of market penetration?
Yeah.
Is the problem.
All right. So generally speaking, larger the capacity, the slower the speed. We can go the other way. The faster the speed, typically the smaller the capacity. Now, what about our needs? Is faster memory always better memory? Well, it depends what we're using it for. Sometimes capacity is more important to us. Sometimes speed is more important to us. And we have to look at it and decide which is important to us at that level. Now, when we're dealing with computer organization, how all of our parts talk to each other, do you think inside of our computer we probably have several different levels of memory that all talk to each other? Okay, so a general thing that we might say here is the closer to the CPU, the faster and smaller memory gets. That tends to be a truth as well. All right, so something, I'm just going to give us one slide here. The memories. So from the CPU, we have something called a register. Super fast. Okay, these are like 8-bit, 16-bit, 32-bit, 64-bit registers. These are really fast. These are connected to the CPU. Then we have L1 cache, L2 cache, L3 cache. Then we have our system RAM. Keep at the high level. Then we have our hard drive. There's some little things in between there, but in general, registers are the most expensive memory per bit, followed by L1 cache, L2 cache. L1 cache and L2 cache live on a single core. L3 cache lives outside of a core, so it's how memory is, how stuff is transferred between multiple cores on a CPU. And we used to have offboard L3 cache, and we had multiple CPUs as well. And we'll talk about these again. I'm just giving you the high level here real quick. RAM, we all know what RAM is, and hard drives, we all know what hard drive is. So we're going to spend a lot of time talking about this stuff. All right, questions, comments, concerns, bribes. Remember, ice cream social thing tonight, extra credit to be a sign-in sheet, blah, blah, blah. Look out for the camp out guy. He's going to flag you in there. What else we got? Books. You probably should start reading chapter 1 from the book. I would say for next class, read up through 1.5. That gets us pretty much where we are right now. So up through 1.5 in the book for next class. Always a threat of a quiz.